subscribe now and press the bell icon. Never miss an update.
Hello, good morning students. If you recollect, we have considered optical instruments to assist the eye. Eye, remember, is the most sensitive organ of the human body, yet it has some limitations in the sense that it cannot see very small objects or very distant objects. For instance, you try to read keeping your book very close to your eye, you can't read it up to a particular point, which we call the near point, and the corresponding distance is called the least distance of distinct vision. If you take away the book beyond a certain point called the far point, you can't read the book. So in between these two, we see the objects very clearly. If you want to see a very small object, let's suppose a dust particle, it's not also possible by the naked eye. So we have the instruments, namely microscopes and telescopes. Now we have considered two microscopes, the simple microscope, it is commonly called reading lens, and also the compound microscope. And people working with microscope, particularly the compound microscope in the laboratories, will have to work for quite a long time. And that strains the eye, you become tired easily. The eye, when it is relaxed, see, it is easy to see for a long time. Now therefore, we usually use microscopes, either simple microscope or compound microscope, in what we call the normal adjustment. The normal adjustment only means that the final image that we see through the microscope is at infinite distance. When the muscles are most relaxed, the eye doesn't get strained. Now with that background, see, we shall go to telescope, astronomical telescope. Telescope, as you know, is a device used to see distant objects, far off objects. Astronomical telescope is used to see astronomical objects like planets, satellites, etc. Now, a common astronomical telescope consists of a convex lens, optic axis, principal axis rather. See, this is called the objective. Now, the object is at infinite distance. Now, therefore, the rays, by the time they reach the eye, the objective, see, will be parallel. And a parallel beam of light, let us suppose, falling on the lens like this. Now is focused at the principal focus. If the beam is inclined to the axis, now the beam gets converged at a point below the principal focus of the objective, F0. So here you have a ray like this, gets converged from the topmost point to the object. So this is the image of the topmost point. Now for every point the same thing holds good. So you have the image, the first image, I1 M1, formed at the principal focus. Now here, see, this serves as the object for another lens, the eyepiece. Now we keep the object, that is I1M1, such that it is within the principal focus of the eyepiece of E. I1M1 serves as the object. Now these are the rays coming from the object. Observe. I do not know how they go out, but I know a ray coming from the object passing through the optic center goes straight. Another ray parallel to the axis, now passes through F here. So like this. Now they do not meet after they go out of the eyepiece. They meet when produced backwards. Like this. Now this is where the final image of the distant object is formed. The other rays, these rays, go like this. All the rays appear to come from, the distant object like this. We see the in an astronomical telescope actually, you have these lenses, you can adjust the distance. We adjust the distance between them such that the final image is formed at a distance of distinct vision. Now this is the position adjustment where we have the image of the distant object most clearly seen. So here, astronomical telescope consists of two lenses, O and E, mounted coaxially in a tube. The distance between them can be varied. The lens O is called the objective, as it is towards the object and has very large focal length. The lens E towards the eye is called eyepiece, and has very short focal length. Now this is the making of the telescope, the construction of the telescope. Now the working. See, the rays from distant object become parallel. By the time they reach the objective. And get converged. At the principal focus, forming an image I1M1. The position of the islands is adjusted such that the image I1M1 is within FE, the principal focus is the islands. I1M1 acts as object for the eyepiece, and the eyepiece serves as simple microscope forming the final image I2M. The islands is adjusted such that I2M2 is formed at the distance of distinct vision, where the lens, the image is most clear. Now, and as I have told you, when the final image is formed at the least distance of distinct vision, the image is most clear. However, see, one has to keep on seeing distant objects, astronomical objects, for hours and hours, if not days long. Now, therefore, usually telescopes are used in the normal adjustment. In the normal adjustment, see, rays from distant object falling on the objective, see, converge, form the the initial image, for the first image, I1M1, at the principal focus of the objective, FO. Now, we adjust the position of the eyepiece such that I1M1 is formed also at FE. In other words, here in this adjustment, the principal focus is the objective, the principal focus is the eyepiece, they coincide, with the result that the object, see, the image which now serves as the object for the eyepiece is at the principal focus. Consequently, rays from the object after coming out of the lens become parallel. So, they appear to come from infinite distance. See, the adjustment is said to be normal adjustment, wherein there will be least strain on the eye. Now, we will derive an expression for the magnification in this adjustment. Now, magnification here is defined as now remember one thing here, if you have the eye like this, let's suppose you have the eye lens, And if an object is placed like this, now this is the image. If the same object is placed here, now this is the image. Observe. If the object is placed here, the image is here. Notice that the size of the object does not change, but as we go away from the eye, the image that we see here goes on decreasing in size. Consequently, see, if it is less than a minute of an arc, we will not be able to see this object at all. Now, therefore, we define the magnification in terms of the angles subtended by the image and the object. So, here magnification is defined as the angle subtended by the final image to the angle subtended by the object. Now, there is a relationship between the image size, see, and the angle, object size and the angle. See, this angle, they are different, the sizes are different, therefore, the definition still holds good there in terms of angles. Now, looking at the figure, see, angle subtended by the image. Now, the image is this. Now, it subtends an angle, let's suppose alpha here. So, that is alpha. And the object is here, it subtends an angle beta. So, it is alpha by beta. Now, this can be written as, for all practical purposes, tan alpha by tan beta. See, for small angles. Now, remember that the object is at infinite distance, therefore, this angle is really very, very small. So, this we can write. Now, therefore, from the figure, see, you have tan alpha, alpha is here, it is I1 M1. This is adjacent side, which is equal to Fe. So, this is equal to I1 M1 divided by I1E whole over tan beta. Tan beta is this I1 M1 again, I1 M1 divided by I1O. Simplifying, see, I1 M1 cancels, giving you I1O divided by EI1. OI1 is F4. I1E, EI1 is Fe. So, this is the expression for the magnification. In the normal adjustment, see, the length of the telescope, OE, that is the length of the telescope. It is OI1 plus EI1, that is equal to F4 plus Fe. F4 plus Fe.